So what I'm going to talk about in this talk is actually what Proxima Centauri B might be like today and how we would go about taking measurements to discriminate what it might be like. And I'll also make the point that what it might be like today is very much a function of the evolution of this planet. And so Rodrigo talked a little bit about what might have happened to this planet, for example, early on. I'm hearing microphone noise. Is that you okay? All right. So as Rodrigo went over, there are several evolutionary end states possible for Proxima Centauri B. We ran through simulations of different initial volatile inventories and hydrogen inventories to see whether or not we could get water to survive, and Rodrigo talked about sort of the probability distribution of that. So the upshot is that water may or may not survive, depending, of course, on the initial volatile inventory. And if Proxima Centauri B formed in its current position, I think you saw that he sort of had a peak near zero water. So it may be more probable that it doesn't have any water left. But if it migrated in or formed with a protective hydrogen envelope, then perhaps it's managed to preserve the volatiles underneath. So when we're thinking about modeling what we might see today, we're looking at potentially very oxygen-rich atmospheres, but this planet is also potentially 5 billion years old, and so we would expect some significant evolution to have occurred. And part of that may, in fact, be evolution towards a more CO2-dominated state for the planet. And of course, we've seen that with an example of a planet that's undergone runaway in our own solar system. And I like to think of Venus as kind of the popcorn of the solar system. It's kind of the end state of terrestrial planet evolution. It's lost at least a 3-meter deep ocean overall, and it has now evolved to be a far more CO2-rich state, primarily because by losing its ocean and having its plate tectonics shut down, that basically removes 2 of the major sinks for carbon dioxide for this object. And so we'd expect this potential evolution of oxygen-rich through the CO2-rich as the oxygen is ultimately sequestered or oxidizes the surface and CO2 is outgassed. And then, of course, we also, because we want Proxima Centauri B to be habitable, we looked at situations where it was much more Earth-like with the rationale that perhaps it had been protected from volatile loss by a hydrogen envelope early on, or it had migrated in. And so the cases we considered were essentially an Earth-like planet, also an early Earth-like planet, so an Archean-like world as well. And we looked at an abiotic O2 world, one in which the ocean had survived and one in which it had not. We looked at a desiccated ExoMars type scenario where CO2 in the atmosphere due to the lack of catalysts had broken down into a stable CO2, O2, CO atmosphere. We also looked at sort of more evolved states, sort of catching it from O2 dominated to CO2 dominated, where we had almost equal amounts of O2 and CO2 in the atmosphere. And finally, we looked at an exovenus, both exovenus light with only 10 bars and a more sort of a classic 90-bar version of Venus. And so we modeled these with coupled 1D climate photochemical models, ATMOS in principle, but we also used our new VPL climate model, which is being developed by well, started out with Dave Crispin, Ty Robinson, but Andrew Lenkowski is now in charge of that, and you heard a talk on TRAPPIST from him earlier this week. But this model has a lot more of the physics in it and allows us to model environments that ATMOS does not. So you can see here the surface temperatures that we have derived with these models. Those in red we consider not habitable, either because of the actual surface temperature or the fact that we're modeling a desiccated planet. Those in green are potentially habitable. No surprise, the Earth-like planets turned out being habitable because that is the definition of the habitable zone, that a planet with an Earth-like atmosphere will be habitable in that zone, and Proxima Centauri sits in that zone. Interestingly, the oxygen-dominated atmosphere with an ocean also turned up a reasonable surface temperature. However, it is very oxygen-rich, and so the question is whether or not life could actually evolve on that type of planet, or certainly if it came out of the oceans, it might get a nasty surprise. So we looked at these overall, and these are our results. And the upshot of this is all really the same planet. This is Proxima Centauri B, but because of its atmospheric evolution, you're looking at very different current atmospheric states, and so consequently a whole slew of different potential surface temperatures and desiccation and volatile states. So because we're running a 1D model and we're looking at a planet that may or may not be synchronously rotating, we also wanted to see how far off we might be by comparing to other 3D GCMs with our 1D model. And these are our results here from the 1D model. These are 3D comparisons with the Turbet et al. With their asynchronous state, so the 3-to-2 spin-orbit resonance. And we actually get within 5 degrees of that. So the 1D model is a pretty good approximation for this relatively rapidly spinning state. Sorry, didn't mean to do that. But if we look at the synchronous rotator here, we're off by about 18 degrees. We're too warm in this particular case. But that's not a huge amount when you're trying to determine whether the planet can in fact support liquid water on its surface. So we get fairly close with these cases. We also looked at whether we would have atmospheric collapse with the scenarios that we looked at. And in the asynchronous case, none of the scenarios we looked at are prone to atmospheric collapse. But the desiccated oxygen-rich ones are kind of on the verge if the planet is synchronously rotating. Okay, and I also want to point out that even though we did this for Proxima B, there was a lot of excitement. We sort of threw all of our tools at Proxima B. It's certainly very relevant also for other planets that have been discovered. So the TRAPPIST, for example, TRAPPIST 1e and F here are kind of in a similar position in their habitable zones. And so the results that we've developed here could also apply to those worlds as well, as well as LHS 1140b too. Okay, so thinking about what we might be able to detect if we have these states, then we are looking at potentially the first thing we might be able to do is with JWST looking at thermal phase curves. And in this case, we could actually try and go after an actual atmospheric compositional detection. These are simulations done by Jake Lustig-Jaeger of the thermal phase curve. In this case, this is the ideal case if there's a very strong day-night temperature contrast. And by that, I mean that the night side is giving off no thermal or negligible thermal radiation. Down here with a 20 Kelvin difference between day and night, it's a little bit more challenging. The true answer is probably somewhere between those. But what you're looking at is if we have an ideal case and there is a strong day-night temperature difference, maybe 10 hours per band per phase to get this using the MIRI instrument. And this is at wavelengths longer than 10 microns because Proxima Centauri B actually saturates at wavelengths shorter than that. So we could potentially use this with JWST to try and go after and not only an atmosphere detection, but also potentially a compositional detection as well. Sorry, I think I've just gone back. Slides are a bit slow. Okay, too far. So we also simulated spectra for these. These are direct imaging spectra, so this is in reflected light, trying to look at how we would discriminate between an ocean-lost planet with abundant O2 versus an O2-rich Earth-like biosphere. The big difference, of course, is the sheer number of bars of oxygen that we're potentially looking at. And in that case, oxygen will collide in this higher density atmosphere and produce collisionally induced absorption. And the O2-O2 collisionally induced absorption is very prominent in both the visible and the near infrared. And so that's something we could look for to try and discriminate something from a more sort of Earth-like classic position with just oxygen here, and you don't see the O2-O2 dimer. It is present in the Earth's atmosphere, but it is very, 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 very weak. We looked at other spectra. I've pressed the button, but it's not advancing yet, that we could look at. So if I can get my slides up, I will try again. Yeah, okay, so the other thing, and this is not a VPL related thing, but I'm extremely excited about this, and this is the potential that we could upgrade instruments, Sphere and Espresso and the VLT, and actually be getting ground-based measurements of the oxygen A band from high-resolution spectroscopy from the ground, and this could be achieved within the next 3 to 5 years as well, so that's another measurement we might want to look at. We also learned some fun things as far as photochemistry and what we might see in the spectra as we were doing this. These are spectra of the O2-dominated worlds, one with an ocean, one without. The desiccated world is in orange, the ocean in purple. These are spaghetti plots. If you're a photochemist, you'll love these. But what I do want to point out here is that in the desiccated case, ozone is able to persist all the way down to the surface, whereas in the more water-rich case, it's actually scrubbed out of the lower atmosphere by the presence of water vapor down there. And that does make a significant difference in the spectrum. We actually see a very strong, this is in transmission, so this would be more likely for the TRAPPIST planets since we're not sure Proxima transits. But in transmission, you can actually see this very strong Chapuis band in the ozone, which is completely missing, in fact, in the desiccated case. And so that's another interesting thing that we look at for that's also a secondary indicator that we might, in fact, have an ocean on this world. So in the next spectra, so we also modeled, of course, a photochemically self-consistent Earth around this planet forced by Proxima Centauri B's spectrum, and we then ran these through simulators that were developed by Ty Robinson, and Jake Lustig-Jaeger did these as well, looking at sort of what we might see in about 10 hours of integration with HabEx here and LUVOIR here. The LUVOIR wavelength range is significantly longer because we're looking at a different inner working angle cutoff for 1 lambda over d over here. What you can see, obviously, from this is a very noisy spectrum at these shorter wavelengths, and that's because we're looking at a late-type M-dwarf where we are not getting a lot of flux. And since we're observing in reflected light, you're just never really going to get a great signal there because there's not, any sunlight falling on the planet there. That makes it harder to try and pick out things like Rayleigh scattering because of that. So in the final example here, this is for Jada, since she's sharing. These are hazy Archean type exoplanets. Jada loves haze. And these haze-dominated worlds actually do have a very strong feature, but again, it's kind of in this zone where it's going to be difficult to observe because of the reflectivity and the low blue component of the star. But what's also very interesting here is the semi-major axes, the inner working angles that we can look at. So this red one here is 1 lambda over d. That's what we'd really like to achieve. This is 2 lambda over d here and 3 lambda over d. So you can see that, again, the scales are different for the different sized telescopes. This is 6.5 meter and this is a 16 meter class telescope. So it will be difficult to observe the haze if we can't get past about 2 lambda over d with HabEx, and hopefully we will with the star shade. We'd be looking at a very short wavelength range and would be stuck in the region where the star is not very reflective. And so again, if a star shade can get us out to here, that would be great, so we can see that particular wavelength range. For Le Voir, if we can achieve 2 lambda over d, we have a fairly good wavelength range to look at as well. So for these particular telescopes, they will certainly get enough flux, but it will be the inner working angle that will challenge whether or not we can get these observations. So I have pressed the button, but I'm not seeing anything. OK, here we go. So in conclusion, we've modeled a bunch of atmospheres that are plausible for this object. So they could be O2 rich initially, becoming more CO2 rich as the O2 is sequestered. These environments could be habitable or not, and it's just interesting to look at the fact that it is, again, the same planet, but these very different environments give us different results. Thermal phase curves may be a good first thing to go after, but we also have a very rich suite of molecules available in the visible and near infrared that could help us discriminate between these different types of environments. And then finally, that although this modeling was done for Proxima B, it certainly could also apply to these other new planets that we are discovering. So I will end there.
Thank you very much, Vicky. We have time for questions.
Hi, Richard Archer, University of Colorado.
Hi.
I was actually wondering about star shade, if you have any update regarding progress, because I was under the impression that at this point that's mothballed or basically in kind of a purgatory.
I don't believe that is the case. Sean, if you would like to answer that question. I know Maggie's probably here too, but Sean would definitely be. Okay, there you go, Maggie. You answer that one.
It's baseline to be, the W first would be star shade ready. But it's not officially included as part of the mission as of yet, and we'll be relying on the decadal survey to be really smart about that and say, yeah, we should fly one.
Right. Yeah. So that's the test with W first. This was for HabEx with the star shade, which is another mission altogether.
And the star shade is baseline for HabEx.
Right. Yeah. So HabEx should have a star shade.
Hi, Alex Pixel, University of Arizona. So you mentioned how these results could be generally applicable to, for example, LHS 1140, because same type of star, same general installation. What about effects of density?
You mean the density of the planet itself?
Yeah, because it's like 3 times as much surface gravity.
Right. So I mean that will change the scale height of the atmosphere and therefore the response to the incoming radiation. So yeah, I guess what I'm saying here is just that there's this general idea that we will have evolved secondary outgassed atmospheres, and some of the phenomena that we're looking for is generalized. But you're right, those individual cases we absolutely go after and model for the specifics of the planet.
Thank you.
Sure.
Hi, great talk. Joe Zaleski, ASU. So you mentioned very briefly the possibility of going after this with current ground-based direct imaging with a few upgrades in 3 to 5 years. Could you touch on that maybe a bit more and explain how you got the 3 to 5 year timeline?
So this is in a paper by Lovis et al., which came out in 2016, and it's proposed upgrades to the Sphere Advanced AO system on the VLT and also the Espresso high-resolution spectrograph. And the time estimates were based on the number of hours they needed to detect the band. If I can get back there, probably not. So they need about 60 hours total, but they also will only be able to get that sporadically, sort of at maximum elongation, and so that has to separate the time at which they can integrate their signal over. And so they will be waiting for a sort of orbital, and it's only an 11-day orbit, but still it's going to extend their time out. So part of that time is the upgrade to the instruments, and the other part is the time taken to integrate to get the oxygen.
Thank you.
Let's thank Vicky again.